Advanced Television Systems Committee standards are a set of standards developed by the Advanced Television Systems Committee for digital television transmission over terrestrial, cable, and satellite networks. The Atsc standards were developed in the early 1990s by the Grand Alliance, a consortium of electronics and telecommunications companies that assembled to develop a specification for what is now known as HDTV. Atsc formats also include standard definition formats, although initially only HDTV services were launched in the digital format. Background: the high-definition television standards defined by the Atsc produce widescreen 16:9 images, up to 1920 x 1080 pixels in size, more than 6 times the display resolution of the earlier standard. However, many different image sizes are also supported. The reduced bandwidth requirements of lower resolution images allow up to 6 standard definition sub-channels to be broadcast on a single 6 MHz TV channel. Atsc standards are marked AX and can be downloaded for free from the Atsc's website at atsc.org. Atsc Standard A53, which implemented the system developed by the Grand Alliance, was published in 1995. The standard was adopted by the Federal Communications Commission in the United States in 1996. It was revised in 2009. Atsc Standard A72 was approved in 2008 and introduces H264 Avc video coding to the Atsc system. Atsc supports 5.1-CHANNEL surround sound using the Dolby Digital AC3 format. Numerous auxiliary datacasting services can also be provided. Many aspects of Atsc are patented, including elements of the Mpeg video coding, the AC3 audio coding, and the 8 VSB modulation. The cost of patent licensing, estimated at up to $50 per digital TV receiver, has prompted complaints by manufacturers. As with other systems, Atsc depends on numerous interwoven standards, e.g., the EIA 708 standard for digital closed captioning, leading to variations in implementation. Digital switchover. Atsc replaced much of the analog NTSC television system in the United States on June 12, 2009, replaced NTSC on August 31, 2011 in Canada and on December 31, 2012 in South Korea, and has replaced NTSC as of September 2015 in the Dominican Republic, December 31, 2015 in Mexico. Broadcasters who used Atsc and wanted to retain an analog signal were temporarily forced to broadcast on 2 separate channels, as the Atsc system requires the use of an entire separate channel. Channel numbers in Atsc do not correspond to RF frequency ranges, as they did with analog television. Instead, virtual channels, sent as part of the metadata along with the program, allow channel numbers to be remapped from their physical RF channel to any other number 1 to 99, so that Atsc stations can either be associated with the related NTSC channel numbers, or all stations on a network can use the same number. There is also a standard for distributed transmission systems, a form of single-frequency network which allows for the synchronized operation of multiple on-channel booster stations. Audio. Dolby Digital AC3 is used as the audio codec, though it was standardized as A52 by the Atsc. It allows the transport of up to 5 channels of sound with a 6th channel for low-frequency effects. In contrast, Japanese ISDB HDTV broadcasts use MPEG's advanced audio coding as the audio codec, which also allows 5.1 audio output. DVB allows both. Mpeg-4 audio was a contender for the Atsc standard during the DTV Grand Alliance shootout, but lost out to Dolby AC3. The Grand Alliance issued a statement finding the Mpeg-4 system to be essentially equivalent to Dolby, but only after the Dolby selection had been made. Later, a story emerged that MIT had entered into an agreement with Dolby whereupon the university would be awarded a large sum if the Mpeg-2 system was rejected. Dolby also offered an incentive for Zenith to switch their vote. However, it is unknown whether they accepted the offer. Video. The Atsc system supports a number of different display resolutions, aspect ratios, and frame rates. The formats are listed here by resolution, form of scanning, and number of frames per second. For transport, Atsc uses the Mpeg system's specification, known as an Mpeg transport stream, to encapsulate data, subject to certain constraints. Atsc uses 188-byte Mpeg transport stream packets to carry data. Before decoding of audio and video takes place, the receiver must demodulate and apply error correction to the signal. Then, the transport stream may be demultiplexed into its constituent streams. Mpeg-2. There are three basic display sizes for Atsc. Basic and enhanced NTSC and PAL image sizes are at the bottom level at 480 or 576 lines. Medium-sized HD TV images have 720 scan lines and are 1280 pixels wide. The top tier has 1080 lines 1920 pixels wide. 1080 line video is actually encoded with 1920 x 1088 pixel frames, but the last 8 lines are discarded prior to display. This is due to a restriction of the Mpeg-2 video format, which requires the number of coded luma samples to be divisible by 16. Most resolutions can operate in progressive scan or interlaced mode. Although the highest 1080 line system cannot display progressive images at the rate of 50, 59.94 or 60 frames per second. Because such technology was seen as too advanced at the time and the image quality was deemed to be too poor considering the amount of data that needs to be transmitted. The standard also demands 720-line video be progressive scan. A terrestrial transmission carries 19.39 megabits of data per second, compared to a maximum possible Mpeg-2 bitrate of 10.08 mbit per second allowed in the DVD standard and 48 mbit per second allowed in the Blu-ray disc standard. Although the Atsc 53 standard limits Mpeg-2 transmission to the formats listed below, the U.S. Federal Communications Commission declined to mandate that television stations obey this part of the Atsc standard. In theory, television stations in the U.S. are free to choose any resolution, aspect ratio, and frame field rate within the limits of main profile at high level. Many stations do go outside the bounds of the Atsc specification by using other resolutions, for example, 352 by 480 or 720 by 480. EDTV displays can reproduce progressive scan content and frequently have a 16:9 widescreen format. Such resolutions are 704 x 480 or 720 x 480 in NTSC and 720 x 576 in PAL, allowing 60 progressive frames per second in NTSC or 50 in PAL. Atsc also supports PAL frame rates and resolutions which are defined in Atsc 63 standard. The Atsc 53 specification imposes certain constraints on Mpeg-2 video stream. The maximum bitrate of the Mpeg-2 video stream is exactly 19.4 mbit per second for broadcast television, and exactly 38.8 mbit per second for the high data rate mode. The amount of Mpeg-2 stream buffer required at the decoder must be less than or equal to 999,424 bytes. In most cases, the transmitter can't start sending a coded image until within a half second of when it's to be decoded. The stream must include colorimetry information. The video must be 4:2:0. The Atsc specification and Mpeg-4 allow the use of progressive frames coded within an interlaced video sequence. For example, NBC stations transmit a 1080i 60 video sequence, meaning the formal output of the Mpeg-4 decoding process is 6,540 line fields per second. However, for primetime television shows, those 60 fields can be coded using 24 progressive frames as a base. Actually, a 1080p 24 video stream is transmitted, and Mpeg-4 metadata instructs the decoder to interlace these fields and perform 3:2 pull-down before display, as in soft teletuning. The Atsc specification also allows 1080p 30 and 1080p 24 Mpeg-4 sequences, however they are not used in practice, because broadcasters want to be able to switch between 60 Hz interlaced 30 Hz progressive or PSF, and 24 Hz progressive content without ending the 1080i 60 Mpeg-4 sequence. The 1080 line formats are encoded with 1920 x 1088 pixel luma matrices and 960 x 540 chroma matrices, but the last 8 lines are discarded by the Mpeg-4 decoding and display process. H.264, Mpeg-4 Avc. In July 2008, Atsc was updated to support the ITU-T H.264 video codec. The new standard is split in 2 parts. 72 Part 1. Video system characteristics of AVC in the Atsc digital television system. 72 Part 2. AVC video transport subsystem characteristics. The new standard supports 1080p at 50, 59.94 and 60 frames per second. Such frame rates require H.264 AVC high profile level 4.2. while standard HDTV frame rates only require levels 3.2 and 4, and SDTV frame rates require levels 3 and 3.1. Transport stream. The file extension, TS, stands for Transport Stream, which is a media container format. It may contain a number of streams of audio or video content multiplexed within the transport stream. Transport streams are designed with synchronization and recovery in mind for potentially lossy distribution in order to continue a media stream with minimal interruption in the face of data loss in transmission. When an over-the-air Atsc signal is captured to a file via hardware, software, the resulting file is often in ATS file format. Modulation and transmission. Atsc signals are designed to use the same 6 MHz bandwidth as analog NTSC television channels. Once the digital video and audio signals have been compressed and multiplexed, the transport stream can be modulated in different ways depending on the method of transmission. Terrestrial broadcasters use 8 VSB modulation that can transfer at a maximum rate of 19.39 Mbit per second, sufficient to carry several video and audio programs and metadata. Cable television stations can generally operate at a higher signal-to-noise ratio and can use either the 1/6 VSB as defined in Atsc or the 256 QAM, defined in SCTE, to achieve a throughput of 38.78 Mbit per second using the same 6 MHz channel. The proposals for modulation schemes for digital television were developed when cable operators carried standard resolution video as uncompressed analog signals. In recent years, cable operators have become accustomed to compressing standard resolution video for digital cable systems, making it harder to find duplicate 6 MHz channels for local broadcasters on uncompressed basic cable. Currently, The Federal Communications Commission requires cable operators in the United States to carry the analog or digital transmission of a terrestrial broadcaster, when so requested by the broadcaster. However, cable operators have still been slow to add ATSC channels to their lineups for legal, regulatory, and plant and equipment-related reasons. One key technical and regulatory issue is the modulation scheme used on the cable. Cable operators in the U.S. can determine their own method of modulation for their plants. Multiple standards bodies exist in the industry. The SCTE defined 256 QAM as a modulation scheme for cable in a cable industry standard, and SCTE 07-2006. Digital transmission standard for cable television. Consequently, most U.S. and Canadian cable operators seeking additional capacity on the cable system have moved to 256 QAM from the 64 QAM modulation used in the plant, in preference to the 16 VSB standard originally proposed by ATSC. Over time, 256 QAM is expected to be included in the ATSC standard. There is also a standard for transmitting ATSC via satellite. However, this is only used by TV networks. Very few teleports outside the U.S. support the ATSC satellite transmission standard, but teleport support for the standard is improving. The ATSC satellite transmission system is not used for direct broadcast satellite systems. In the US and Canada, these have long used either DVB-S or a proprietary system such as DSS or DigiCipher2. Other systems. ATSC coexists with the DVB-T standard, and with ISDBT. A similar standard called ADTBT was developed for use as part of China's new DMBT-H dual standard. While China has officially chosen a dual standard, there is no requirement that a receiver work with both standards, and there is no support for the ADTB modulation from broadcasters or equipment and receiver manufacturers. For compatibility with material from various regions and sources, ATSC supports the 480i video format used in the NTSC analog system, 576i formats used in most PAL regions, and 24 frames per second formats used in film. While the ATSC system has been criticized as being complicated and expensive to implement and use, both broadcasting and receiving equipment are now comparable in cost with that of DVB. The ATSC signal is more susceptible to changes in radio propagation conditions than DVB-T and ISDBT. It also lacks true hierarchical modulation, which would allow the SDTV part of an HDTV signal to be received uninterrupted even in fringe areas where signal strength is low. For this reason, an additional modulation mode, enhanced VSB, has been introduced, allowing for a similar benefit. In spite of ATSC's fixed transmission mode, it is still a robust signal under various conditions. 8 VSB was chosen over COFDM in part because many areas are rural and have a much lower population density, thereby requiring larger transmitters and resulting in large fringe areas. In these areas, 8 VSB was shown to perform better than other systems. COFDM is used in both DVB-T and ISDBT, and for 1 seg, as well as DVB-H and HD radio in the United States. In metropolitan areas, where population density is highest, COFDM is said to be better at handling multipath propagation, while ATSC is also incapable of true single-frequency network operation. The distributed transmission mode, using multiple synchronized on-channel transmitters, has been shown to improve reception under similar conditions. Thus, it may not require more spectrum allocation than DVB-T using SFNs. A comparison study found that ISDBT and DVB-T performed similarly, and that both were outperformed by DVB-T too. Mobile TV. Mobile reception of digital stations using Atsc has, until 2008, been difficult to impossible, especially when moving at vehicular speeds. To overcome this, there are several proposed systems that report improved mobile reception. Samsung, Rohde & Schwarz's AVSB, Harris, LG's MPH, and a recent proposal from Thomson, Micronis. All of these systems have been submitted as candidates for a new Atsc Standard, ATSC-MH. After 1 year of standardization, the solution merged between Samsung's AVSB and LG's MPH technology has been adopted and would have been deployed in 2009. This is in addition to other standards like the now-defunct MediaFlow, and worldwide open standards such as DVB-H and TDMB. Like DVB-H and ISDB1-SEG, the proposed Atsc mobile standards are backward compatible with existing tuners, despite being added to the standard well after the original standard was in wide use. Mobile reception of some stations will still be more difficult, because 18 UHF channels in the US have been removed from TV service, forcing some broadcasters to stay on VHF. This band requires larger antennas for reception, and is more prone to electromagnetic interference from engines and rapidly changing multipath conditions. Future Atsc 2.0. Atsc 2.0 is a major new revision of the standard which will be backward compatible with Atsc 1.0. The standard will allow interactive and hybrid television technologies by connecting the TV with the Internet services and allowing interactive elements into the broadcast stream. Other features include advanced video compression, audience measurement, targeted advertising, enhanced programming guides, video-on-demand services, and the ability to store information on new receivers, including non-real-time content. Atsc 3.0. Atsc 3.0 will provide even more services to the viewer and increased bandwidth efficiency and compression performance, which requires breaking backwards compatibility with the current version. Atsc 3.0 is expected to emerge within the next decade. On March 26, 2013, the Advanced Television Systems Committee announced a call for proposals for the Atsc 3.0 physical layer, which states that the plan is for the system to support video with a resolution of 3840 x 2160 at 60 fps. In February 2014, a channel sharing trial began between Los Angeles Television Statins KLCS and KJLA, a commercial ethnic broadcaster, with support from the CTIA and approval of the Federal Communications Commission. The test involved multiplexing multiple HD and SD sub-channels together, experimenting with both current Mpeg-2 H262 and Mpeg-4 Avc H264 video codecs. Ultimately, it has been decided that H264 would not be considered for Atsc 3.0, but rather the newer Mpeg-HHEVC H265 codec would be used instead, with OFDM instead of 8 VSB for modulation, allowing for 28 megabits per second to 36 megabits per second or more of bandwidth on a single 6 MHz channel. In May 2015 and continuing on for 6 months, the temporary digital transition transmitter and antenna of Cleveland, OEO's Fox affiliate, WJW, will be used by the National Association of Broadcasters to test the Futurecast Atsc 3.0 standard advanced by LG Corporation and Gateshead. In September 2015, further tests in the Baltimore and Washington, D.C. area were announced by Sinclair Broadcast Group's Baltimore station, WBFF. The Futurecast system had previously been tested in October 2014 during off-air hours through Madison, Wisconsin ABC affiliate WKOW. Unlike Atsc 1.0, 2.0's distributed transmission systems pseudo-single-frequency network operations, WI9XXT's two transmitters operate as a true single-frequency network.